Hey, day 11, y'all. You know it's day 11. Another one, another day, another dollar. So yeah, what's up? Today we're gonna do something, as you can see, indoor. I'm gonna slow jog, and I'm going to do some neat code. It's a video that's on basic data structure and algorithm problems. Same drill as last time. And I get my remotes near me. I have on my watch. I have a black shirt. This shirt I got from a coach in 2016. It still fit me. My bro gave me this for my birthday this year. Big up. And shoes, same basketball shoes. Nike Air Lacoste. Yeah. I'll show you at the end. But yeah, we're outside, we're doing it. I mean, we're inside. And we're doing it right. For all the people in tech, we're gonna be listening to some neat code videos today. This is our practice course for elite code programming, or coding questions. And I'm on the Fibonacci sequence lecture. It's going to talk. So how does it is? This guy named neetcode on YouTube. Pretty cool. He's been breaking down interviews in different sections. Like, okay, here are key questions that you have. He has this thing called neetcode 150. Yeah. Anyways, yeah, he breaks down the problem first, or breaks down the data structures first, and then jumps into the questions afterwards. So you'll hear something simple and then something more difficult. So we talk about arrays, we talk about linked lists, we talk about doubly linked lists, queues, factorial already. Now, you know, recursion stuff we don't know. Then we're going into sorting, binary search, and all that different type of searching algorithms. Trees, backtracking, heap next. Then last but not least, hashing graphs and dynamic programming. But I don't think we'll get to that. Today we're just going to be listening to this. I'll stop and watch and try to recount. I wish I had a whiteboard. Well, I can't whiteboard and slow jog at the same time. But anyways, we're here trying to be productive at the same time. So I'm turning this up. And I'm also turning my TV up. Alright, cool.
Is equal to n, roughly speaking, it's equal to n because that's the height of the tree, right? If we're taking this and then doubling it and then doubling it.
Well, yeah, remember people,
which gives us
they're out here each and every day trying to do
but
better.
if we do it like this, we're going to go
to run, because honestly,
more interesting.
it's something that you can do to keep yourself accountable by videoing yourself. Reminding you, hey, you need to get up. Before this, I was on the couch, really just being a couch potato, as they say, because I'm tired, man. But because of this video thing, I said, you know what, let me get up and try to push myself to come. So now, I'm here, at least 10 minutes. So let me start let me do 5 minutes first. And I know that I won't stop now, even after 5 minutes pass. So, do the tactic, do it for your work, do it for your love life. You know, sometimes you feel like, I don't know, it don't happen to me, but if you ever feel as if you don't want to get into something, so, you know what, open your mind, just get into it. 5 minutes. And you don't know, it might be there the whole day. Or you do it for your work, do it for your cricket. If you're batting, you say, you know, let me be out here for 5 minutes at least. Do it for your football. Let me just start passing the ball for 5 minutes, get into it. And then start doing more stuff afterwards. Keep it simple, 5 minutes. And then you get into the groove. But we're out here and we're pushing. I'm going to start this thing on my watch right now. We're running. And that says 5 minutes. Starting here now. And remember, zone 2, zone 3 is the target. Right now we're at 2.6 miles per hour, 3.2, 3.4. So I'm going.
case of two-branch recursion.
Oh,
And let's use another math example. In this case, let's calculate the Fibonacci numbers. Now, the general formula to calculate the nth Fibonacci number is to take the n-1 Fibonacci number and the n-2 Fibonacci number and add them together, which gives us the nth Fibonacci number. But if we do it like this, we're going to go on forever if we try to calculate like can stop. Well, we do have some base cases for us to find. The 0th Fibonacci number is 0. The first Fibonacci number is 1. So using this, what would the second Fibonacci number be? Well, it would be the n-1 Fibonacci number, which is 1, plus the n-2 Fibonacci number, which is 0. And we know that these are defined as a part of our base case. This is 1, so 1. This is 0, so plus 0. That means the second Fibonacci number is equal to 1. So now we have that. Then we can compute the third Fibonacci number, which we know is going to be n-1. That's 2 plus n-2, that's going to be the first Fibonacci number. So now we have the second Fibonacci number, which is 1. We have the first Fibonacci number, which is also 1. So this is equal to 1 plus 1. So therefore, the third Fibonacci number is 2. Now the way I'm calculating right now is very straightforward. I'm pretty much looping through these, and we could go as high as we want. We could now calculate the 4th, the 5th, the 6th Fibonacci number, but this is not recursion. The recursive solution for this problem is actually less efficient, but I still want to show it to you because it illustrates for us two-branch recursion. So let's say we want to calculate the 5th Fibonacci number. This is where our decision tree is going to get very useful. Maybe we can't immediately compute this, but we know this can be broken up into a couple sub-problems like n-1 and n-2. So to compute the 5th Fibonacci number, we can compute the n-1, which is 4, and n-2, which is 3. But for either of these branches, we still haven't reached the base case yet, which we know is 0 or 1. So let's continue down the left path. This can also be broken up into a couple sub-problems, again n-1 and n-2. So n-1 would be 3, n-2 would be the second Fibonacci number. For this, it's going to be n-1, which is the second Fibonacci number, and n-2, which is the first Fibonacci number. Now let's continue to draw this out. So the third Fibonacci number can be broken up into n-1, which is the second Fibonacci number, added with the first Fibonacci number. To get the second Fibonacci number, we can get the first Fibonacci number added with the 0th Fibonacci number. It's starting to get a little bit messy, but we're almost done. So over here, the second Fibonacci number, which we sort of just did over here, is also going to have two steps, which is the first Fibonacci number added with the 0th Fibonacci number. Now over here, do we also need to break this up into subproblems? No, because we finally reached our base case over here. So now to take a quick preview at the code, the base case we know is going to be either 0 or 1. So we could have an individual case for each of these. We could say if n, the input, is 0, then return 0, and if it's equal to 1, return 1. But we can condense that into a single if statement. If n is less than or equal to 1, that means that it's either 0 or 1, then return n. Because when n is equal to 1, we're returning 1. When it's equal to 0, we're returning 0. So whatever it is, that's what we can return when it's less than or equal to 1. But for the recursive case, as we've been doing, we know we have to compute the n-1 and the n-2 Fibonacci number. And then when we have those, we're finally going to add them up and then return that integer value. But we're not quite done yet. We know that this here, the first Fibonacci number, it is 1. So that's what I'm going to put here. And actually, we've reached the base case with all of these, but there's just one branch left for us. So let's quickly complete that one, and then we can compute the result. So the second Fibonacci number we know is n minus 1, which is 1, plus n minus 2, which is 0 in this case. So adding these together will give us the second Fibonacci number. So now going down this path, let's say, for n minus 1, we're going to end up returning 1 in our code over here. For 0, we're going to end up returning 0. And then we're going to be back up here in our decision tree. For this, the code we're going to be at is this return code. We've computed n minus 1, which turned out to be 1. We computed n minus 2, which turned out to be 0. Now we're adding them together, 1 plus 0. So we're going to end up returning 1 from here. And this was also a base case. So recursively here, we would have executed this line of code and we would have ended up returning 1. You can see that it might not be easy to know what's going on just by looking at the code, especially when you get to 2-branch recursion and beyond that. That's why we draw out these decision trees, which make it relatively simple. So we know to compute the third Fibonacci number over here, we get the results of the 2 paths. We were first computing the second Fibonacci number, which turned out to be 1, and the first Fibonacci number, which turned out to be 1 as well. We add those together, so we add the return values from here, and then we return 2 from here. So now we're trying to compute the fourth Fibonacci number. First, we needed to compute the third Fibonacci number to do that. We did that here. Now we need to get the second Fibonacci number, and to get this, we get its sub-problems, the first and the 0th Fibonacci number, which both are, well, this is 1, and then the 0th is 0. We add those together, that's going to be 1. So from here, we return 1. So to get the fourth Fibonacci number, we have 2, which is the third Fibonacci number, and 1, which is the second Fibonacci number. We add those together, and we return 3. Now at this point, you're probably starting to get the idea. So finally, to get our original result, which is the fifth Fibonacci number, we needed to compute the fourth Fibonacci number. We did that. We have 3. And now we need to compute the third Fibonacci number. And to do that, we need to get the second and the first Fibonacci number. And to get the second Fibonacci number, we need to get the first and the 0th, which are going to be 1 and 0. Add those together. We get 1 as the second Fibonacci number. Add this and this together. We get 2 as the third Fibonacci number, and then add this and this, we get 5 to be the fifth Fibonacci number. It's gotten very messy here, but we did finally get our result. And again, this is definitely not the most efficient way to solve this problem. Earlier, we were doing it with a loop. So to get the nth Fibonacci number with the loop technique I was talking about, the time complexity would be big O of n. But here we've drawn it out recursively, and clearly this is not big O of n. So to analyze the time complexity of this recursive solution, looking at the code is not going to help us a ton. The picture is a lot easier to use, but it's going to require a bit of math. First, to get the fifth Fibonacci number, or just some general nth Fibonacci number, we have to break that up into 2 sub-problems, right? And then those 2 sub-problems have to be broken up into 2 more sub-problems each. And then those sub-problems might need to be broken up into 2 more sub-problems, unless, of course, we've reached the base case, which for this one, we have reached the base case. But in general, for each of these, we might have to break it up into 2 more sub-problems. Now, the fact that we have to break it up into 2 sub-problems comes from the fact that we have 2 branches in our recursive tree. But in this recursive tree, how many times are we going to have to break it up into 2 steps? In other words, what is the height of this decision tree going to be? The height is basically how many levels does this tree have. You can see 1, 2, 3, 4, 5, levels. That makes sense because for the path where we have 5, then we have 4, and then to get that we have to go to 3, then to 2, and then to 1. That's what the longest path is going to be. So the number of layers in this decision tree is going to be n, where that's the nth Fibonacci that we're trying to compute. Now this is the part where I could get overly technical if I wanted to, but I want to try to keep it simple in terms of math. So in general for us to get the number of Fibonacci values in the last level, theoretically with math, it would be, we start with 1 and then we double every time. So it would in theory be 2 times 2 times 2, and the number of terms that we would have is equal to n. Roughly speaking, it's equal to n because that's the height of the tree, right? If we're taking this and then doubling it and then doubling it, the number of times we double it is going to be n, and that's the same as the input value. So to get the number of values in the last level is going to be roughly, let's say, 2 to the power of n. Now in this case, we can see that the last level only has 2. So in reality, this is actually an upper bound for the number of values we could have in the last level. It's not the precise value, it's an upper bound. But what we know about this last level is the same thing we talked about earlier in math. When you have a series like 1 and then 2 and then 4 and then 8 where you're doubling it every time, this is special in math. It's called the power series. It's always dominated by the last term. So 8 is going to be greater than or equal to all the previous ones combined. If we add a value 16, it's going to be greater than or equal to all the previous combined. So what I'm saying here is that this is an upper bound for the last level. That means it's also an upper bound for the total number of values in this decision tree. If you don't believe me, well, remember, we can multiply this by any constant. So we say, let's say our constant is 2. So 2 times 2 to the power of n is still, in terms of big O time complexity, equivalent to 2 to the power of n in terms of big O time complexity. Precisely, though, it would be n plus 1. But remember, we don't care about constants when they're multiplying or adding to variables. So 2 to the n plus 1 is equivalent to 2 to the n minus 1 as well, right? In terms of big O time complexity, all 3 of these are equivalent. So this is essentially a long explanation for saying that 2 to the power of n is how we can bound this in terms of big O time complexity. Even though this isn't the precise number of values in this decision tree that we drew, it's still a very good upper bound, because remember, we don't care about constants like +1 or -1. And this idea of 2 to the power of n is something we're going to continue to see throughout the course. It all comes from that idea of math, from that idea of power series. 2 turns out to be a very special number for computer science and math.
Nice. Recursion! So we just did the infrastructure part of it. Now we do an interview. We do a question.
So this is going to be another dynamic programming problem, and this is definitely more on the easy side, definitely compared to some of the really hard dynamic programming problems that we've been solving recently. But I still think that this is a good problem to really understand the fundamentals, understand, the brute force, and taking that brute force, using memoization, and then of course getting the true dynamic programming solution. And by the way, if you don't already know, we have been tracking a list of blind 75 questions on this spreadsheet. So today we're going to be solving this dynamic programming one, the climbing stairs problem. So I will be adding the solution once this video is uploaded. And the link will be in the description if you do want to take a look at this sheet. So the problem statement is pretty simple. We're climbing a staircase and it's going to take us n steps to reach the top of the staircase. Every time we take a step, we have 2 choices of how we can take a step. We can either just take one single step, or we can take 2 steps at once. And all we want to know is how many different ways can we get to the top of the staircase. So let's look at the first example, n equals 2. That means we need to climb 2 steps. So we could draw the picture kind of like this, right? So let's say we start over here, right? This is step 0, basically, when we haven't climbed anything. Our goal is to get up here, which clearly is 2 steps, right? So starting from here, we know we can make 2 choices, right? We can take 1 step and that would land us over here, or we could take 2 steps and that would land us over here. So already we're seeing one way is to just take 2 steps, right? That's what this path would take us, right? That's one way we could reach the goal, right? Just taking 2 steps at once. Now, if we ended up taking 1 step, then we would be at this position. So from here, we would have that same exact choice, right? We can take 1 step, or we can take 2 steps. Now, clearly, if we take 2 steps, we've gone too far, right? We were only trying to climb 2 steps total, but if we, end up over here, then, that's not going to count as a path, right? So that would not count. But as you can see, if we took 1 step initially, then we could take another single step, and that would be another way. So either this is one way we could reach 2 steps, or we could just take a single double step, right? So clearly there are 2 different ways we could climb the staircase, and that's also the result of this problem, and they basically explain it over here. So let's look at the second example, which is basically if we're climbing 3 steps instead of 2, right? So let's look at the drawing. So once again, we're gonna do the exact same thing that we did, right? From here, we could take 1 step, or we could take 2 steps, right? And so far we get here, but remember our goal is to climb 3 steps, so let's continue. So from here, we could take 1 step, which would land us at the result, or we could take 2 steps, which would get us out of bounds, right? That's not what we want to do. So far we have found one way to get us to the result, but let's continue that from over here. Again, we can take a single step, which would get us over here, or we can take 2 steps, which would get us at the result. So now we've found 2 different ways we can get to the last step. And lastly, we still have a path to continue, right? We got here by taking 1 step and then taking another single step. So here we have 2 choices: take 1 step, get to the result, or take 2 steps and get out of bounds. So in the end, we see that there were 3 different ways we were able to get to this last step. As you can see, this is getting really hard to visualize with a single staircase. A more easy way would be to get a decision tree to visualize. And at every decision, remember, we can take 1 step or we can take 2 steps. Well, so let's try to visualize the problem like that and see if we can notice any patterns. So let's say we're given n equals 5. We're trying to climb 5 steps. So we can consider, just like the previous drawing, that we're starting at step 0 and our goal is to get to step 5. Now remember, at every given point, we have 2 decisions to make. We can climb 1 step or we can climb 2 steps, right? And depending on the decision that we make, each of these is going to lead to a different path we can take to get to the result. And remember, all we're trying to do is count the number of ways we can get to that result. So in this decision tree, we're going to keep making 2 decisions at every step, and at the end, we're going to count how many different ways were we able to get to 5 steps reached. So we can get to step 1 and we can get to step 2. Let's just continue drawing out the decision tree. From here, we can make 2 more decisions. We can take 1 step, which would get us to 2. We can take 2 steps, get us to 3. And similar here, we can take 1 step, get us to 3. 2 steps, get us to 4. From here, we can also take 1 step, get us to 3. 2 steps, get us to 4. 1 step, get us to 4. 2 steps, get us to 5. Now here, we can see that we reached the result, right? N equals 5. So this is our first path that we could reach to get us to the result, right? You can see we took 1 step, then we took 2 steps, then we took another 2 steps. So this is our result. Once we get to it, that's our base case, right? We're going to solve this recursively, right? That's pretty much what we're doing. This decision tree is basically recursion, and this is our base case. We wouldn't want to continue if we got here. So here we would return 1. We found 1 way to get to the result. But for the remaining paths, let's continue. So here we could take 1 step or 2, that gets us to 4. This would get us to 5. So you can see once again, we found another way we can get to the result. So far we have 2 different paths that can lead us to step 5. And here, let's do the same thing. If we take 1 step, we get to 5. That's the result. If we take 2 steps, we get to 6. That means we overshot, right? We went too far. This is another base case. If this number of steps ever exceeds 5, then we're going to return 0, right? We found 0 ways from this path that can reach the result. So now let's continue. Over here, again, we take 1 step or 2, so we'll get to 4 or 5, another path that leads us to the result. And here we can also take one step or two, which would get us 5 or 6. Similarly over here, right? This is another 4, so the exact same thing is going to happen. You start to see we're repeating the exact same problem multiple times. How can we better solve this problem knowing that? So now we have another 4. We're just going to repeat the exact same thing that we just did before, right? Take one step or two. We know we're going to get to a 5, and we know we're going to get to a 6. So you can see every path led to the base case except for this last one. So let's complete this. We can take one step, which would get 5, or 2 steps, 6. Okay, so now our entire decision tree is complete. So what's the result going to be? Remember, red means we're going to return 0. Green means we're going to return 1. So let's just count the number of greens. 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 different paths from the beginning that could reach step 5. But remember, since we started here, we were asking how many different ways starting at 0 can we get to 5? And then we got to a subproblem. We got to a subproblem of starting at step 1, how many ways can we reach 5? From this decision tree alone, we see that there's 1, 2, 3, 4, 5 different ways we can reach the result. And down 2, if we're starting at step 2, there's 3 different ways we can reach the result. Now, if you solve the problem like this, basically using recursion, and you could probably do it with depth first search, because this is basically a tree, and what would be the time complexity of that? Well, clearly you can see that we have 2 decisions each time, so it's going to be 2 to the power of the height of this tree. What's the height going to be? It's going to be roughly n equals 5, right? You can see that this is going to be the longest path, so that's roughly the height. So the overall time complexity is going to be 2 to the power of n. That's not super efficient, but you can see here, we're repeating the same problem multiple times, right? When we get over here, we're asking how many different ways, starting from 2, can we get to 5, right? And down in this decision tree, we found, yes, there were 3 different ways, right? So then when we get over here, why do we have to recompute the exact same thing? Take a look at these 2 purple blocks I just drew. Notice how this decision tree looks the exact same as this one, because in both cases, we're solving the exact same subproblem, and since we're doing it depth first search, this one is going to be solved first, right? So if we solve this entire problem, what we said was, okay, we found out starting at step 2, there were 3 different ways to get to step 5. So when we get here, why don't we just take that result, store it in memory, store it in DP, or basically this is a cache, right? We're storing it in memory, so then when we get here, we can just say we already know the result of this, meaning that we don't need to draw out the entire decision tree. We're just gonna skip that altogether. We're not gonna draw this, we're not gonna draw that, and we're not gonna draw any levels of this tree. So as you can see, I'm eliminating all that repeated work by saving that solution. But that's not all, right? We see over here, we're asking a different subproblem. Starting at step 3, how many different ways can we get to n equals 5? Well, in this case, it was 2 different ways, right? Notice how this decision tree is the exact same over here, because here we're asking that same question. Starting at step 3, what's the number of ways? And since we're doing this depth first search, this one is going to end up being computed before this one. So when we get here, we can just say we already know the answer is 2. So we don't need to run through the entire decision tree again. So in this case as well, we can eliminate that repeated work. So I'm just going to cross this entire thing out. And we're not done yet. See over here, we're asking starting at step 4, how many ways can we get to 5? That same problem is over here. Notice how they have the exact same decision tree. This one is going to be computed first because we're doing depth first search. So once again, let's eliminate this repeated work. So now you can see when we do eliminate all that repeated work, this is what our decision tree ends up looking like. And this is roughly O of n. This is linear time solution. Reason being, we're only solving each subproblem once, right? So we know that the first subproblem, the original problem is starting at 0. Then we get a subproblem of 1, 2, 3, 4, all the way to 5, which is our base case, right? So each of these subproblems is just being solved once. N is 5, so overall the time complexity is big O of n. And this is basically the dynamic programming solution where we are caching the result, aka memoization. So we're using memoization. But this problem can actually be solved with a true dynamic programming solution. As you can see, starting at the result, the result of 0 depends on the subproblem, this one, right? And this subproblem depends on another subproblem, which depends on another subproblem, which depends on another subproblem, which depends on our base case. So why don't we start at the bottom, solve the base case, and then work our way up to the original problem at 0, right? Why don't we start at the bottom, work our way up? This is called a bottom-up. This is called a bottom-up dynamic programming approach. So that's what I'm going to show you. We're going to start at the base case and then work our way up. So remember, we're starting at position 0, and our goal is to get to the 5th step, right? Each time we can take 1 step or we can take 2 steps, right? So I'm going to be storing our result in an array called DP. So we're going to have a position in DP all the way from index 0 all the way up to index n, which is going to be our input value, remember? So remember, we're at the base case initially, right? What's the base case going to be? Well, at the last step, if we start here, how many different ways can we land here? Well, that's just going to be 1, right? That's our default value. So now that we solved that, we are able to solve this one, right? Because remember, this problem depends on the subproblem of this. So from here, let's say we're starting here, we can take 1 step, which lands us at the result. We can take 2 steps, which lands us out of bounds, right? So how many different ways from here can we reach the goal? Again, it's going to be 1. And you notice how this is always going to be the case, even if we had something like n equals 100. So let's say this was actually 100 and this was 99. This would always be 1, right? This is always going to be 1 because it's at the goal. And starting from here, it's also always going to be 1 because we can take 1 step, which would get us to the result, or we can take 2 steps, which would get us out of bounds. So no matter what the input value n is, this is always going to be the case. It's always going to be 1, 1. Next, we're going to get to the interesting part. So then we want to know, okay, how many different ways from here can we reach 5? Well, this depends on 2 subproblems which come after it, right? So we can take 1 step over here or 2 steps over here, right? So, and then we get to the subproblem, right? So from 4, we don't need to continue to figure out how many different ways from 4 can we get to 5, because we just computed that. That's why we're using dynamic programming. That's why we have this array, because we already computed, starting at 4, how many different ways can we reach 5? And we also, starting at 5, how many different ways can we reach 5? That's also 1. So what we're going to do in this value is basically take these next 2 values, add them together, 1 plus 1, and then we're going to get 2 over here. And we're going to do the exact same thing for this position too. So we know here we could take 1 step or 2 steps, right? So what we want to do from here, 3, is find out how many different ways can we reach 5. We just computed that, that's 2. And from 4, we want to know how many different ways can we reach 5. We also already computed that, that's 1. So what we can do is take these 2 values, add them together, and that's going to be what we put here. So starting at 2, we can get to 5 3 different ways. And at this point, I bet you probably get the idea. We're going to do the exact same thing over here. So what value are we going to put over here? Just take these next 2 values, add them together. 3 plus 2 is going to be 5. And remember, this is what we were originally trying to compute. This is going to be the result. It depends on only 2 subproblems, which are listed right after it. 5 plus 3, that's going to be 8. So that's the result. If you're familiar with what the Fibonacci sequence is, the Fibonacci numbers, that's exactly what we're doing right now. We're starting at the base case of 1, 1, adding these 2 values to get the next result, then we're adding these 2 values to get 3, then we're adding these 2 values to get 5, then we're adding these 2 values to get 8. So you may or may not be familiar with it, but that's what we're doing. And you may have also noticed we're using extra memory, right? We're having an entire array size equals n. That's going to be O of n extra memory. But is it actually needed to have an entire array? Notice how each value, such as this one, only depends on the 2 values that come after it. And this one only depended on the 2 values that came after it. So in reality, we don't need to have an entire array. We just need to have 2 different variables. Let's initialize the 2 variables like this. 1 is going to be this position, 2 is going to be this position, because starting from here, we want to know how many different ways could we reach the result. If we took one step, that's why this is called 1. And if we took 2 steps, that's why this is called 2. And we're basically going to be computing this next value, right? And once we compute this next value, we're going to shift our 1 variable over here, and we're going to shift our 2 variable over here, and we're going to keep doing that until we get to the result of 0. And if we initialize 2 initial variables, 1 and 2, as values 1, how many different values do we have to compute that come after it? In this case, you can see we have to compute 4 values, right? So basically we compute n minus 1 values. We have to loop n minus 1 times, and then when our 1 variable ends up getting in this position, that's what we're going to return as the result. So this was a really long explanation because we did a lot of analysis, but when I actually show you the code, it's going to be really simple using this idea of 2 variables being shifted n minus 1 times. So as I said from the drawing explanation, we're going to have 2 variables, 1 and 2. Both are going to be initialized as 1, and then we're just going to loop through n minus 1 times. So for I in range n minus 1, and we're going to continuously update these 2 variables 1 and 2. So the first thing I'm going to do is update 1. 1 is going to be set to 1 plus 2, right? Because we're just adding the 2 previous values and then getting the new result. So 1 is being updated, and we would also want to shift 2 to whatever the previous value of 1 was. But you can see that we're updating 1 before we actually shift 2. So what we're actually going to do is store 1 in a temporary variable before we actually update it, and then we're going to set 2 to the temporary variable so that we don't end up setting it to 1 plus 2. We just want it to be set to 1, so we're going to set 2 equal to temp. Once this loop goes through n minus 1 times, we're going to end up just returning whatever 1 happens to land on. And that is the entire solution. We went through so much headache just to get to these 5 lines of code. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
That one, the underneath, watch out then. Dynamic program.
A ton of different sorting algorithms, all with their own trade-offs. It's usually applied to arrays like this one, but you can also apply it to other data structures, including linked lists and others. So in this case, we have an array of 5 values, and clearly they're not in order. They're not in ascending order, which would be in increasing order, like 1, 2, 3, but they're also not in decreasing order, which in this case would be 6, 4, 3, etc. Suppose we want to sort them such that they are in ascending order. So our target array would look something like this, 1, 2, 3, 4, 6. We can achieve this with the insertion sort algorithm. Let's see how we can do it. Well, the main idea is to break the problem into subproblems again. So if we want to sort the entire array, the first thing would be to have the first portion of the array, meaning just the first element, have this sorted. Well, one value, like 2, is sorted by default. I mean, how could this be not sorted if it's just one value? So we consider any array of one value to be sorted. The next thing to do, the next subproblem, would be to sort the first 2 values. Make sure these are sorted, and then have the first 3 values sorted, and then have the first 4 values sorted, and keep doing that until we have the entire array sorted. So thinking of it this way in terms of subproblems makes the algorithm a lot more simple. Now, since we are doing it with subproblems, technically if we wanted to, we actually could solve this using recursion, which is a technique we just learned, but it's not really useful in this case, so I won't do it. We can do this without recursion, aka we can do this iteratively. We can have an iterative solution, which is using loops. Now the idea is we're going to loop through the array, but we're going to start at the second element because we know that this subarray is already sorted. So starting here and assuming that every value before this position, meaning this subarray, is already in sorted order, our goal now is to have this array be sorted. So our goal really is to figure out where to put this value. We already know all of these are sorted. Where should we put this one in terms of this array? In this case, we don't have a lot of choices. The logical thing to do is compare this value to the only other value in our array. Is this larger? If this is larger, then it should stay where it is. If it's smaller, it should be swapped with the value over here. Since this is larger, it can stay here. Now there's the other edge case where what if both of these are equal? If that's the case, this value can also stay here because it doesn't matter whether this goes here or here if they are both equal because it will be sorted either way. This is for ascending order, but it would work the same way with descending order as well. So now that we know where this value should go, it should stay where it is, we can now move to the next value. So by the time we get here, we know that this subarray is already sorted. So at this point, we're going to do a similar comparison. We're going to compare this to its left neighbor. Is 4 greater than 3? Yes, it is. So it's going to stay exactly where it is. And at this point, we didn't even compare 4 to 2, but we don't need to. Do you know the reason why? Well, we already know these were in sorted order. So if 4 is greater than 3, of course it's going to be greater than every value to the left of 3 because these are sorted. Every value to the left of 3 is going to be less than or equal to 3. And now every value to the left of 4 is going to be less than or equal to 4. So at this point, we know that these values are in sorted order. We can shift our pointer to the right by 1 over here, and now things are going to get a little bit interesting. So now we have this sorted portion, and we have to figure out where the 1 should go. Should it go at the end of these 3 values? Should it go in between these 2 values? Should it go in between these 2 values? Or should it go over here? Well, let's see what the algorithm does. This is why it's called insertion sort, because we're taking one value and inserting it into a sorted array. So let's see what the algorithm does in this case. First, we're going to compare 1 to 4. Is 1 greater than or equal to 4? It's not. So now we finally execute the other case. And by the way, the pseudocode for this would look something like this. Remember our pointer, which is I, in this case, started at index 1, and we're going to keep going until we've reached, the end of the list. So that's pretty straightforward. And now we're going to get to the interesting part where we compare this to the neighbor. So we have a second pointer for the neighbor. We call that j. This is at I, or you could also call this j plus 1. That's what we're going to be doing. And then you compare these, and now the value at j plus 1 is less than the value at j. That's this part of the code. This part is basically to make sure that we don't go out of bounds, and you'll see what I mean in just a second. But now that this comparison holds, we're going to perform the swap. This is where we take this value and move it over here, and take this value and move it over there. So the first thing we would do actually is take the value that was originally at j plus 1, which is 1, and put it in a temporary variable, because what we're going to do is now at this index j plus 1, we're going to move the value that was here. So we're going to put a 4 over here. And then over here, now that we've lost the 1, we have to use our temporary variable. So we're going to put a 1 over here from our temporary variable. And originally our j pointer was over here. We're going to decrement it by 1, which means we're going to shift it to the left by 1 over here. And the reason this is a while loop and not just an if statement is because now we're going to continue this whole process. We originally have the 1 over here, and we know it should be shifted to the left because it's definitely less than 4, but we don't know that we're done. We don't know that this is the final spot that this 1 is going to be. We have to continue comparing to the left neighbors. So now we're going to execute the condition again. First, we're going to make sure that j is not out of bounds yet, because as we keep shifting it, we know at some point it's going to be all the way over here. It could be out of bounds, but right now it's not out of bounds. We know that because it is greater than or equal to 0. And now we're going to compare the value at j plus 1 to j. J plus 1 is less than the value at j. 1 is less than 3. So now we're going to do the exact same thing. We're going to perform the exact same swap. So now we have our 3 over here and our 1 over here, but we're not done yet. We're going to decrement our j one more time. So now j is going to be over here. It's still in bounds. And the value at j plus 1 is again less than the value at j. So now we're going to do another swap. So the 2 is over here and the 1 is going to be over here. And now j is going to be shifted to the left by 1 again. Now it's out of bounds. So now there's no point in even doing a comparison. That's why we're checking that it's in bounds before we do this. We don't want an index out of bounds error. So since it's not in bounds, we can stop doing this loop. And we know now that our I pointer, by the way, was over here. So now at this point, our I pointer is going to be shifted over here because we're going to execute the next part of the for loop, the outer loop that's over here. And we know because of that, this portion of the array, these first 4 values are now in sorted order. And they look sorted as well. 1, 2, 3, 4. So now that our I pointer is over here, our j pointer is going to be initially over here. J is in bounds. So now let's compare the two values. Is 6 less than 4? It's not. So we know that this is greater than 4. Therefore, it's going to be greater than all of these as well. So that means that this is already in sorted order. Our outer for loop is now going to stop because there's no more elements over here, left for us to traverse. Now we've been talking about sorting integers so far, but of course this could be applied to characters if we had something like B, C, A, as long as we have a way to compare characters. So in this case, let's say we're sorting based on just alphabetical order. We can basically sort any set of values as long as we have a way of comparing two values together. So in this case, we could sort these to be something like ABC. Of course, we could also sort strings themselves the same way a dictionary sorts words. So a word like apple would go before a word like banana. With sorting, there's also this notion of stable versus unstable sorting. Let's say we had this array of values, 7, 3, 7. Any sorting algorithm is going to take these values and would be preserved. These two would stay in the order they were in originally. So based on this implementation, this is a stable sorting algorithm. It's preferred to keep an algorithm stable if you can. We could code this in such a way where it's not stable, but that would have no benefit for us. So we're going to keep it as stable. So now finally, let's talk about the time complexity, like banana. With sorting, there's also this notion of state. First 7 could have gone here, and then the second 7 would have gone here. Or they could have been in reverse, right? This 7 could have gone first, and then this 7 would have gone second. Both of those are valid sorting order, but a stable sorting algorithm will preserve the original order when there's a tie. We know that there's 2 7s, and for some reason, if we wanted the original relative order of these 2 7s to be preserved, meaning this one showed up first before this one, so it should go first in sorted order. That's called stable sorting. Unstable sorting might achieve this, but there's no guarantee. It's not necessary that that will be preserved, so it could have flipped them for some reason. We'll touch on this again as we continue, but my question for you, based on this, do you think the insertion sort algorithm is stable or is it unstable? Well, let's quickly go through how it would execute on this. First, our pointer would be over here. We would compare the 3 and the 7. They're out of order, so we would swap them. So then our first 2 values would look like this. So that's good so far. And then our third pointer would be over here, right? And this would be a 3 and this would be a 7. And we would say, this 7, is it less than the 7 on the left of it, right? That's where this would execute. This 7 is not less than that, so it's going to stay exactly where it is. So therefore, we would achieve this output where the relative order in case of a tie would be preserved. These two would stay in the order they were in originally. So based on this implementation, this is a stable sorting algorithm. It's preferred to keep an algorithm stable if you can. We could code this in such a way where it's not stable, but that would have no benefit for us. So we're going to keep it as stable. So now finally, let's talk about the time complexity, which is interesting for insertion sort actually. And the best way to actually understand it is to look at a couple examples. Let's say we were running insertion sort on a list that's already sorted. What would the algorithm do? Well, we would have a pointer over here. We would want to, of course, iterate through the array, but then we would do a comparison. From here, we would compare it to the left neighbor. They're already in sorted order, so we don't have to do anything. We can shift our pointer over here. We compare these two values. They're already sorted. We don't have to do anything. We shift the pointer again. Then we compare these two values. They're already sorted. We don't do anything. We shift the pointer. We're out of bounds. That means we're done. So as you can see, when we have an array that's already sorted, we run insertion sort, and the execution is just iterating through the list, which is big O of n time complexity. Of course, we have nested loops here, but just because we have a loop here doesn't mean it's necessarily going to execute. I just showed you an example where this inner loop is never going to execute. So in this case, the best case time complexity is big O of n. Now technically big O means worst case, so I'm kind of misusing it here, but it's kind of common for people to talk about it this way. But in this case, I'm saying the best case time complexity, which would occur when the input is already sorted, is going to be linear time complexity. Let's look at the other case, where is the worst case time complexity, which would actually occur on the opposite example, where the input is in reverse order and we want to sort it in ascending order. So in this case, again, we would loop through the array. We would start here. We would compare the two neighboring values. We would see that they're out of order, so then we would have to swap them. We would put the 3 over here and the 4 over here. Then we would shift our pointer over here, and then we would compare these two values, and then we would see they're out of order. We'd have to swap them again. We would have to put the 2 over here and the 4 over here. And at this point, we're still not done yet. This 2 is going to be compared to its left neighbor now, and they're again out of order, so we would have to put the 3 over here and the 2 over here. So you can see it's definitely getting messy, but ultimately what we would find is we would have to take this 3, shift it over here. Then we would get our pointer over here, this 2, we would have to shift it here, and then we would have to shift it here. Then when we get to this 1, we would have to shift it to the left, then shift it to the left again, and then shift it to the left again. So for every single value that we iterate through, the inner while loop would have to execute the maximum number of times until that value is shifted all the way to the left. When we get to the 2, we'd have to shift it all the way to the left. When we get to the 1, we have to shift it all the way to the left. Now for an input size of 4 in this case, n squared time complexity would look like 4 squared, because the length is 4, which would be something like 4 plus 4, right? Added together, how many times? Well, 4 times. That's just the math formula here. But this isn't that. What we were doing right now was actually a bit different. What we actually have is something like 1, and then plus 2, and then plus 3, and then plus 4, because for this value, we might have to, consider it to be in these 2 positions. For this value, it could be in these 3 positions. For this value, it could be in these 4 positions, which correlates to that 4, and I just talked about the 2 and 3 case. And we might not have a 1 case, because remember, we're skipping the first index, but again, this is just an approximation, and that's enough for us when we're doing big O time complexity. Now, what most people do when they have nested loops, they automatically assume that the time complexity is big O of n squared, and usually it's the correct assumption, but I bet most people don't know why that's the case. And I'm going to explain it to you briefly right now. This equation is bounded by n squared. It's pretty obvious when you look at it like this, because every term here is greater than or equal to every term here. But I'm going to show it to you in terms of big O time complexity, where remember, we know that constants don't matter when we're multiplying by a variable, right? So some constant c times n squared doesn't matter regardless of what the constant is. I'm going to use this idea to prove it to you that this is bounded by n squared, 3 over here and the 2 over here. So you can see it's definitely getting messy, but ultimately what we would find is we would have to take this 3, shift it over here. Then we would get our pointer over here, this 2, we would have to shift it here, and then we would have to shift it here. Then when we get to this 1, we would have to shift it to the left, then shift it to the left again, and then shift it to the left again. So for every single value that we iterate through, the inner while loop would have to execute the maximum number of times until that value is shifted all the way to the left. When we get to the 2, we'd have to shift it all the way to the left. When we get to the 1, we have to shift it all the way to the left. Now for an input size of 4 in this case, n squared time complexity would look like 4 squared, because the length is 4, which would be something like 4 plus 4, right? Added together, how many times? Well, 4 times. That's just the math formula here. But this isn't that. What we were doing right now was actually a bit different. What we actually have is something like 1, and then plus 2, and then plus 3, and then plus 4, because for this value, we might have to, consider it to be in these 2 positions. For this value, it could be in these 3 positions. For this value, it could be in these 4 positions, which correlates to that 4, and I just talked about the 2 and 3 case. We might not have a 1 case, because remember, we're skipping the first index, but again, this is just an approximation, and that's enough for us when we're doing big O time complexity. Now, what most people do when they have nested loops, they automatically assume that the time complexity is big O of n squared, and usually it's the correct assumption, but I bet most people don't know why that's the case. And I'm going to explain it to you briefly right now. This equation is bounded by n squared. It's pretty obvious when you look at it like this, because every term here is greater than or equal to every term here. But I'm going to show it to you in terms of big O time complexity, where remember, we know that constants don't matter when we're multiplying by a variable, right? So some constant c times n squared doesn't matter regardless of what the constant is. I'm going to use this idea to prove it to you that this is bounded by n squared, and I'm not even going to use a math proof. Now, maybe I'm not smart enough to show you the math proof of why this is true, but I'm smart enough to draw a picture, and that turns out to be enough. We know that n squared, where n is 4, would look something like this in terms of geometry, right? 4 times 4, right? This is us having to iterate through an array of size 4 times. We have to do that. We have to iterate through it once, twice, 3 times, 4 times. But we also have the case where we iterate through just, let's say, the first value of the array, and then the first 2 values of the array, and then the first 3 values of the array, and then the first 4 values of the array. So maybe now it's becoming a little more obvious why this is bounded by this. And not only that, this is actually pretty much exactly half the size of n squared. And we even talked about how the first term in this case doesn't actually apply. So maybe this isn't even there, but it's still, you can see, approximately half the size of n squared. We didn't even use a math proof to figure this out. This is obvious enough from looking at a picture. So if this is half the size of n squared, we can write it as n squared divided by 2, or in other words, 1/2 times n squared. And this is just a constant, remember, and we don't care about constants. So we can say this, or in other words, iterating through an array like this would be the same as big O of n squared time complexity. That's the worst case time complexity of insertion sort. So that was a lot to cover, but to finally wrap up our first sorting algorithm, insertion sort, which is a stable sorting algorithm, has a worst case runtime of n squared, but it's also worth mentioning that the best case runtime is big O of n. That's not always true for other sorting algorithms, but it does turn out that there's better sorting algorithms than n squared worst time complexity.
Okay, y'all. We're at the end of this video. Of 1.5 minutes left. Today we learned about Fibonacci sequence. Just simple, but we learned the dynamic programming equivalent for our climbing stairs problem. It's a little bit wonky in my brain, so I'm gonna run it back and try to code up the solution myself. I forgot how DP worked fully. I know some memorization take place where it basically solves it like a Fibonacci sequence and then store the value in a hash map or some array just to make it quick retrieval of the data that you previously calculated. But the full DP solution was a little bit wonky for me. Typically small lines of code, but a lot of thinking went into it in terms of the analysis and how it ended up working. And then the next thing was insertion sort. Everybody know that work. You go through the array and you swap the part that is already sorted with the part that you're currently looking at. So once you visualize that initially, and remember that the neighbor section, you keep going down and swapping. It's not too difficult. But anyways, we're here. Those are the two that we saw. We're thriving, keep running, keep being accountable. Even when you're on the couch, you feel like you're sleeping and you can't move or step out. 5 minutes is a start, and then take it from there. Alright, cool. 13 seconds left. Thank you all for watching. Anyways, I saw that I got 6 subscribers. 35 of you watch the videos and only 6 subscribe. Stop what you're doing and subscribe. Big up Ryan LFC. That's his spiel. But it's gonna become my spiel. Stop what you're doing and subscribe, like, and share. Alright? Big up on yourself. And y'all saw when I almost fell. And that was rough. But we endured. Thank you all for watching. And soon. Woo. Hey!
Hey! Hi, Dr. Listin.
Tell them to watch your video. Tell them to watch your video.
Hi.
Day 11.
This is Kevin White for representing Kevin White. And I'm telling you to like, share, and subscribe with Dappa runs. Stay tuned.